Santosh. Yes. So with the objective of power system and control, we again put some light on this. What is the main objective with which power system is designed, put in practice, and made to operate? That is stated as an objective. Objective of the power system control strategy is to generate adequate active and reactive power and distribute it to an interconnected system as economically as possible. Being very reliable in operation, maintaining the frequency, voltage within the specified limits which are put as a control parameter, and adequate changes in the requirement be met suitably, keeping the resources optimally utilized and leaving them for the future. This is the exact objective of the power system, which has coined and collected all the parameters with the interest of generation perspective, operational aspect, delivery, satisfactory levels of end user, all together in concern to the resources available and usage of them without fail. Along with this, when the system is put in practice by the interconnection of several types of generator, transmission mechanisms, switchgears, and variety of end users in the form of load, operation is very dynamic. Off and on, in meeting all these objectives stated, system encounter difficulties. Those difficulties, if I put together under the three great headings as stability point of view, security point of view, and reliability point of view. System has to see to it that in meeting the objective of the stated parameter, it should be stable in operation. When I say the word stability, stability is the ability of the system to be in synchronism even after encountering defects, faults, threats, challenges, etc. Maybe natural or accidental, which are creating the difficulties. System must be protected, proof, able to cope up, maintain its operating point within the specified range, so that that becomes ability of the system. With the perspective of voltage, when I speak, voltage stability. Other way we speak, voltage instability. With respect to frequency, when I speak, frequency instability or frequency stability, I can characterize. Again, the stability aspect with a time frame, a short, medium, long range, I can characterize it. In overall, stability of entire interconnected system is very necessary. It is always challenged by the components. Those components put in practice, encountering difficulties, internal failure, external failure, influence of the phenomena or any natural calamity will definitely threaten the system in that perspective, so that system must be such a way interconnected and put with the control, it is able to cope up and able to be in system in operation. That we coin as stability. And another aspect of security, when I speak about, whenever we install a system or equipment and interconnected operation, definitely due to so many dynamics, so many parameters concerned to the operation and their variation, surely system is challenged. If the system is able to cope up, deliver required active and reactive power being in operation, any contingent variations what would occur can definitely damage the system operation. Service transmission lines may be broken, generators stall, switchgears fail, transformer do not provide sufficient output. Like that, any of the situation, security perspective is another important aspect which is a threatening. When I view the security, security is an expectation from the operational point of power system from all the interconnected components to be in practical service for which they are intended and installed. Surely they encounter overtravel, overload, and contingent changes in their delivery pattern, during which do the component or the connected system is safe to operate, remain in operation even after encountering that difficulty or defect, or is it safe to isolate it? Such kind of aspects, when we look forward, that come under security. It is most important aspect of the operation of the power system, because when the objective which is put to generate adequate active and reactive power and deliver to the end user reliably, it is definite to that system is open for such challenges at every moment of its operation. Maybe a single line failure, line to line fault, anything failure, internal failure of the generator or external failure in that line, definitely challenge the system, and the system, the component which gets affected, if it is fully faulty, surely it goes out of the control and rest of the system are again burdened. Think of a cascaded failure. It will leave the remaining system in danger. Therefore, security aspect must be viewed very carefully and assessed in the energy control center as a separate algorithm, which will keep the visualization of state of health of the power system from security perspective of view of the power system. When I view a power system simply as an operation, as an interconnection, it's a bare view of interconnection. Simply I view a generator by their capacity and range in working, it becomes a capacity range only. When I view especially the particular interconnected system from the perspective of how secure is this for a contingent variation in the load, for the fault, for the expansion of the system is considered for the growth of load in the near future, or from the modernization perspective of such, it must be properly viewed, planned and worked out. Therefore, it cannot be ignored. Similarly, reliability. Reliability, when I view, it is the system's ability to be in practical delivery. It is the probability of the system's delivery or probability of availability of a certain component or a certain system to deliver and to meet its requirement or its service to the needy space or requirement. Whether it will be there to serve you or not. Then this is called probabilistic view of the power system operation. I was just thinking and telling about security perspective. The another term reliability is probabilistic approach to understand and evaluate availability of certain component, certain generator, certain transmission line to meet the requirement of the end user at a certain time of operation. Will that component be there or not? What is the probability that certain identified component will not be there for your service? It is called failure. That kind of mathematical evaluation is done in reliability approach. Again, I propose this is another engineering aspect which must be done without fail. I can predict and I can anticipate what is going to happen in the next 2 days, next 4th day, 7th day, and whatever the upcoming day of the operation of the particular component, how the component is going to behave, its behavior pattern, its service ability pattern, its availability, unavailability, I can understand clearly from single component, multiple components together in a system as I can define system reliability. Do this entire system connected by so many sub-components inside together represent string reliability. All were healthy, system will be healthy. Any one of the major components in the system is unhealthy, which is a crucial player. Definitely other components, if they were healthy, they cannot cope up for a system efficiency or reliability. In that view of the system, reliability is another important mathematical analysis, evaluation of the system's state, which is badly required. So that is one of the important tasks performed in the energy control center of the power system, which is to evaluate the state of health, anticipate what is going to happen, and what are the countermeasures one would take, initiate against such occurrences, etc. Hence, these three factors are very important, and in fact, we have two separate chapters itself addressing security aspects and reliability aspects in this semester as well. And viewing this in another view, how the various controls in the power systems are put by a block diagram. The block diagram in which the dotted rectangle or a square, which looks is a generator unit, which is having a generator, a prime mover control, and excitation system to provide field requirements of the generator. For this mechanism to function appropriately, it requires control. That control signals arise from this particular scheduling mechanism, which is system generation control, load frequency control, and economic dispatch. This is a decision from the energy control center, which is taken to have this generating setup to function as required. For that, again, input stimulus are what is the required standard operating frequency, what is the tie line power flow from this unit to the next unit or from the next unit to this unit, what is the interaction power and scheduling of this particular generator. What is the set point of this generator I am going to obtain, PG, and how long, with what generator, till what duration, that's called schedule. All these schedules, all these parameters combined together to set up a stimulus to the exact mechanism generator system, which control the prime mover, which control the input to the particular turbine, which will drive the generator. This generator, when it is being driven, definitely generate electricity. Once it generates electricity, it has to have RPM feedback to control, which is nothing but frequency control. We have a specific frequency requirement, but to attain that certain frequency, the RPM of the turbine has to be managed. Then speed is fed back. Along with that, terminal voltage, megawatt power are our other important parameters, which are taken into excitation control mechanism. Again, in the module number 2, we have a separate study called as generator loops. We have automatic voltage regulator loop, automatic load frequency control loop, which are nothing but the magnified version of this block which I am trying to convey you. So that you will see there specifically what is that inside the excitation control, how is that speed feedback makes the load frequency management you will be interacting there. Right now for us, when the generator is being driven by a prime mover, the speed feedback becomes one of the primary input to regulate the valve so that the RPM of the generator is managed to reach our required certain frequency. As well, the voltage and power output is fed to the excitation system, which will convert these two parameters into field current for the field of the generator so that the terminal voltage is maintained at stated value. Later, it delivers the power to the grid, wherein transmission control, voltage control, volt ampere reactive control, HVDC, and flexible AC transmission system, etc. will look forward for frequency output, tie-line power flows, power flow out of this generator, etc. This means for a simple generating unit to generate a certain megawatt and be in synchronism, it requires a command. It requires a stimulus, which has to be from the generation schedule, which has to reach this and make the prime mover appropriately controlled, and the output of which connected to the grid, which from which we measure these parameters for our monitoring. This is just a control mechanism, how it is viewed into power system. Then when I move forward, key concepts of reliable operation. When I say the power system be always reliable, why we expect it? When the service is rendered to the end user always expects continuity of delivery of power. Naturally, the dependency of this grid is greater. If you think of in a process industry where continuously machine to machine and machine to group, and there is an interconnection of flow of raw material to the finished goods, if there is an intermittency in delivery of power supply, definitely part of the components in semi-finished stage get lost. They may not be able to reach the destination, and they may not be in a proper stage to get connected to the next. There could be a lot of loss. Then reliability becomes very necessary. It is just not for the industry, for every aspect of interconnection, continuity of delivery of power supply is very necessary. In that perspective, some of the key concepts of reliable operation are outlined here. The one is power generation transmission capacity must be sufficient to meet peak demand for electricity. This parameter, if I see, it is a capacity constraint. When I see a load curve on a particular generating station, the number of generator or a generator which is installed to take care of that has to be such a way installed, it is able to generate the required capacity in an easy way. It should not starve. It should not struggle to generate the required load on that. If it is so, you must have alternative plan to make cope up of that requirement properly. The power system to be reliable in operation, the first and foremost requirement is the ability to generate required power. I should have sufficient number of generator of suitable capacity put in system. That is the first requirement to make the system able to cope up for the requirement. Next must be, power system must have adequate flexibility to address variability and uncertainty in demand and generation resources. This is known as dynamic behavior. Load is continuously changing with the time, and resources are scattered around the geographical position. Depending upon the availability of the resources, suitable generation has to run and generate adequate megawatts from that. The deficit generation has to be cope up with the remaining type of generator so that net generation meets the demand properly. There should be a flexibility. This keyword demand, the ease of operation, integration, removal, additional megawatt demand, rejection, all such facility, freedom must be there in the system so that system will be surely one of the supportive elements for the reliable operation. When I look forward with this parameter, economics of operation, how economic is this particular generator right now? Right over a day, next 2 days, next 1 week, like that if I project it, whether it is costlier to produce a megawatt from that, cheaper to produce a megawatt from that. When I take a decision, I must be capable of removing it if it is costlier, cheaper if it is possible to accelerate and make it generate more and more. I should have a flexibility. In that way also you can see. If the resource is diminishing, coal mines or coal stock in the yard is diminishing, then I must be able to switch my generation to hydro or any other alternative, or anything which I can integrate, I can remove, or I will be able to see load curtailment is also possible for me. In that perspective, if I operate, my system will be reliable in meeting the end user requirement to the expected reliability. The power system must be able to maintain steady frequency. So in the earlier class, we were interacting, frequency sensitive loads are going to suffer if deviation is beyond certain delta F specified for the system. Because the frequency deviation, the change in frequency definitely affects the inductive loads. If the variation is higher and inductive loads unnecessarily absorb higher power for doing nothing, that will cause a pulsation, additional loss, additional heat to just get into other side of the not required. Therefore, frequency must be maintained very suitable. So, the power system must be able to maintain voltage within acceptable range. This was another important aspect of the power system to maintain the steady state voltage within the range, because much of the electrical equipment installed and working in the power system together work at a certain specified voltage. Their functionality is dependent on input supply. If there is a greater change in supply or input with which it is working, definitely the functionality of the system or that component is challenged. It is sure to malfunction, deteriorate in its performance. The values what it is going to project to you may not be of your satisfactory range. Hence, it is surely in the bracket I can say malfunctioning. Such an information, if you are carrying forward for your decision activity or connected to the next stage of decision processes, definitely it is going to carry wrong information and protruding into next good state or causing it to get adversely affected. So therefore, it is another challenge. It must be appropriately worked out to be reliable in operation. The aspect of reliable operation shall be thermal rating must be kept in account and be considered. It's very sure. The thermal rating must be kept in account and be considered. Look forward a certain transmission line. A certain transmission between buses for a long distance or a distance L kilometers. It has a certain ability to transfer MVA and it is having a certain thermal ability. As the current flowing through that increases, I square RC, the transmission line suffering losses and temperature rise will cause thermal failure, thermal breakdown. That conducting material will not sustain further due to its thermal failure. In that due regard, the capability of that transmission line be explored to the good value and beyond certain thermal ability, critical value I should not load. Or if there is a criticality, bottleneck issue associated with that particular component as a thermal rating is considered, I must be taking care of that fact whenever that component is undergoing such an situation, encountering a criticalness. It should not be overridden. It should be controlled well within so that its service is there for the power system. Else, undue overriding of which may cause failure, breakdown of that component, may make its effect cascaded in the next and some other components get affected due to the failure of the first and second together in the third or fifth. The series of failure would result. Therefore, thermal rating of every connected equipment must be considered. I gave an example of transmission line. Why not it is a transformer? Why not it is a generator? It's all the connected equipment must be appropriately monitored for their properness for the thermal rating is considered. It shall not be simply overridden. Else, the encountering or other riding factor will dominate. The next important parameter is system stability be maintained. So as we were interacting, stability with respect to voltage and frequency, and in terms of time stamp, small scale, medium and large scale, and transient ability, it must be there. System must be able to cope up any such contingent variation which are threatening it to get disturbed. If that is not there inherently, system is not going to sustain in its service. In that due regard, the designer has to take appropriate measures, controls such that stability of the power system will never be challenged to the extent designed. Therefore, stability with respect to voltage, which is voltage stability, stability with respect to frequency, frequency stability, which the certain variation and beyond should not be allowed. If the fact which is causing it to vary should be isolated so that rest of the system is protected from such possible impacts of variation. This is an intelligence control mechanism being installed so that system stability is always maintained and good in nature. Otherwise, the reliable operation, continuity of delivery cannot be spoken. Next one is meet N1 criteria. Somebody read it with N-1 criteria, somebody with N1 criteria like this way. What is the meaning of this? Meet N1 criteria. This is a simple, very interesting fact. In an electrical system, when it gets interconnected by N components, N component may be 100 or 200 or 1000. Any of the component among the N in number, suppose go out of service, fail due to internal or external or maybe anything. That component is not there for your service. How is that rest of the system going to behave? That is studied under meet N1 criteria. N1 criteria when I apply to a particular transmission system. In a transmission system, power from a certain generating grid getting transmitted to the transmission line and receiving at the receiving station and to be distributed. Imagine so many transmission sections between bus 1 and 2, 2 and 4, 4 and 7, 7 and 9 like that. Transmission lines are running down in kilometers of length. Suppose out of the total 1000 transmission line sections, one of the transmission line is broken due to its open circuit fault. Let's say that line is not there for delivery of power. Then during that situation, how is that rest of the system minus the one which is out is going to behave? During such situation, which are all the lines getting burdened additionally to deliver the power alternatively via next route or a next possible path of the shortest possible. In that due regard, N1 criteria is very sensible. If any one of the crucial components in the system fails, then the behavior must be such that system is able to cope up even after the loss of that. In this criteria, if I want to narrate one case, we all very clearly know what we mean by spinning reserve. With respect to generating aspect of a system, spinning reserve is a spare energy available in the system by all the generator, what the megawatts they are generating, and what the loads which are drawing, what the losses which are being met. After having the transaction done, there is some extra generated energy spare that we call as spinning reserve. It may be hot reserve or a cold reserve, again by characteristics. Let us make it as a reserve. That reserve is readily available, which is such a way by quantity megawatt. Certain generator suddenly collapse must be able to meet that. Or certain generator is suddenly reduce its capacity to half or certain value by megawatt. This spinning reserve value designed or kept spare by the operational aspect is able to cope up that loss immediately. In that way, a N1 criteria with respect to generator, with respect to transmission line, with respect to other components, I can define and keep my system ready to cope up during such situation. Now you can look forward. This can be one of the important steps for assessment of the security of the system and reliability of the system. So it need not be N1, it can be N2, it can be N3. It means if two components of the interconnected N components fail, two are not there for service, remaining system is in there. How it is going to behave? Its performance, its reliability, its adequateness at that delivery of power. If I study, system must be capable of working out. That's what meet N1. Basically, anyone says how it is going to behave. It should be there to serve you. That is the requirement. So it must be designed like that. The next point is to be more and reliable in operation, prepare for emergency. When the word emergency arrives, look forward for the states of operation of power system. So normal state, an alert state, emergency. During such situation, if the system from alert, if I ignore further, enter with a multiple component going out of your control and system is suffering, and any wrong decisions taken on emergency state would lead to extremities, in extremities or extreme emergency wherein disconnection, failure or partly or fully is highly possible. For that, what are all the countermeasures, counter actions to bring the system from the emergency back to alert and back to normal? We have to list down, initiate, train, keep as a remedial. That's called prepare for the emergency. It is always like that. As we speak of dynamic, any moment an emergency may be there, like a war field battlement, the military force. They are always ready for the emergencies. Any criticality if it is raised, they are sure to get into the situation and act according to the situation required. In that way, how the word emergency is defined by English, it is truly for such an electrical emergency in the power system operation and control is considered, system must be provided with a certain mechanism and procedure to act on a situation to bring at least to the safer point of operation. In the next slide, I have list of some activities which are titled under the emergency and preventive measures, which will definitely be always practiced by the power engineer to bring the system in healthy state. Next one, plan, design and maintain to operate reliably. This is very interesting fact. Once the power system is designed and installed and put in practice with certain objectives, it is not dynamic. Off and on it keeps having challenges and threats always raised against its operation. And the load is one of the important aspects, keep always growing. I must plan and I must think any extensions possible, any rejection, removal, modernization, any correction to keep the system's health appropriate and make it efficient in its functionalities is always an expectation of the good operation. Therefore, a plan, design and maintain to operate reliably shall mean in broad terms keeping the healthiness in the system's operation, planning for the adequate modification, implement any rejection, detection, any correction if so required to keep the healthiness of the system's operation, so that quantifies system's value by reliability. It ensures the state of availability of every component for every moment of time. Hence, it enhances the reliability of the system. So, in that way, all these key points expect or make the reliable operation system. When I look forward with some measures, how measures are taken into the power system such that a good operation is always expected and seen. Some of the preventive and emergency controlling strategies or procedures which are listed over here. As we are very clear, this can be one good question for you in the examination. Preventive and emergency control. The preventive keyword is nothing but as and when there is a chance of certain situation which is going to occur likely, before it occur, if you counteract and make some measures, preparedness to which the impact of such an occurrence is reduced or eliminated. We call it as preventive measure. Prevention is better than cure, how the slogan strikes to us. The same way, preventive measures are the ones which are remedial for any certain adverse effect, adverse scenario likely going to strike on the power system's operational aspect before it is going to become quantified. If I initiate a certain measure in part or full, the magnitude of impact of such an event is certainly diminished, which makes the system healthier. In that regard, these are the preventive measures one should initiate in the system. Emergency controls, when I say, these are the ones which are really seeing the fact. Emergency, how it is announced. Emergency in the civil living, you can just see. It is defined as and when there is flooding, as and when there is a disaster, as and when there is an uncontrolled scenario, emergency state is declared like that. The emergency controls are the one in power system where the alert state of the power system operation states enter into an emergency wherein controls have not been exercised properly and system is suffering running boundary at boundary. Transformers are fully loaded and tap settings are reached the maximum and transmission lines are running over because we are not taken a proper distribution, rescheduling, reorganizing, curtailment of load. Something has not been planned. Suddenly, system has entered to an emergency. Likely, any further contingent variation are sure to damage the system. In which, how emergency control should control the system slowly in steps back to at least an operable. That is how these are. After having seen the facts, influences, we take measures. Not to have further such effects, if we reduce such impact, we take emergency control. Let us see how it is characterized. Preventive control is meant to keep the system in normal state or bring it back to the normal state from alert, which I was interacting with you. Some of the activities like rescheduling of active power generation by variation to match the changing load. How is that system enter alert state from the normal? When I say normal is the state where all the capacity constraints and the limits of any capacity value or equality constraints are well within the range. Certain load variation is occurring, demand is increasing, but the demand is noticed and being served. So rescheduling can help so that it becomes again a normal. Changing the set point of a generator is just an action. So, under the preventive, load is increasing. Do not lead further. Just go back to the generator and make the generator set point change so that the set point will be new one. Along with the new one, operation is controlled appropriately. Like that, rescheduling of generation at units to match the changing load is the best preventive measure if there is a load growth. Startup of generation unit and providing adequate spinning reserve. Suppose the generation is insufficient. Load growth is tremendous in increased steps. Definitely existing generators cannot cope up. And what is the intelligence in which? Before it is rising, today it is rising tendency is noticed. Over a week of time, load growth is going to become a tremendous on the generating station. Today only I should plan, start another generator from the code, bring it online, make it readily available for us to join me at the 4th day or 5th day for my schedule. That way, startup of generation unit providing adequate spinning reserve. Floating energy for a contingent change in load must be planned. Before it really makes sense that there is a net demand higher, that time rather than scratching our head, I should keep remedial. By the time it is needed, it is ready to serve you. This way, the preventive mechanism help us to make the requirement fulfilled. Then switching off shunt elements for reactive control. Remember, any reactive power, switch on, switch off if required, so that reactive power management must be appropriately controlled. As we are very much aware, there is a direct connectivity between active power and frequency, reactive power and the voltage. Anything which the voltage you are not able to maintain is an indicator that reactive power in the system is insufficient. Reactive power cannot be generated like active power and transmitted over a long distance. There is a demerit of that. It must be suitably worked out at the point of requirement. Hence, if the voltage which you are not able to maintain well within the specified range, we have to identify root cause for that. What is the compensating point where if I apply the compensator or switching elements like a compensator, capacitive element, inductive element as required, which will definitely shift the working voltage difference. This is a preventive control, which you are able to manage before really it demand you. Hence, it must be planned properly. Change of reference point of controllable devices such as flexible AC control and transmission mechanism. Fact devices, which is nothing but for the reactive power and voltage control, the power electronic substitute is fact. Flexible AC transmission system, flexible AC transmission system controller. So these provide sufficient active and reactive power supplements as required. Basically, these are meant for reactive power and voltage, which will be in system to support the requirements of active and reactive power balance. So these must be tuned properly, adjusted such that their action on the power system and the elements which are interconnected balance the requirement appropriately. If I speak something TCR, thyristoride controlled reactor, TSC, thyristoride switched capacitor, TCFCR, thyristor controlled capacitor, like that. So many components are there under the heading fact devices. Those devices have to be installed as suitable to their location as required, and their set point need to be properly tuned so that the changing dynamic load will definitely be counteracted by such a controller. It may be phase shifting transformers, etc. like that. All together come under the reactive power and voltage control. Before really it is going to cause a tremendous effect, I as an operator can initiate these things to come in action so that such an impact will not arise. Prevention is already taken by this kind. Change in the voltage reference point of generator and voltage control device. This is an impedance which we were saying generator is unable to boost its required voltage to a certain PU, per unit voltage. Then make the set point change, excitation control or the particular generation input field I can control then and there only. It means to say change the voltage references. The reference point, when I said a certain generator is 11 kV, is generating 11 kV. We are generating 11.6, 11.4 like that kV initially at the generating point. When it is generated and connected to a transformer and pumping it to the grid, it will definitely be reduced. In that due regard, where there is a facility, flexibility, freedom of change in set point should be adopted before really it is demanded by the requirement. That's how which the flexibility we have needs to be encashed. Then change the bus substation configuration like bus bar, splitting, etc. It is nothing but rather than drawing a single conductor to run and make a branching here and there, we can scientifically split the routing of power at the substation, reconfigure, change the connection map pattern, reroute it such that such an event will cause your better operation in the system level. Otherwise, simple old connection, tapping from the multiple points, making a joint and other things may unnecessarily cause disturbances, sparks, arcs, burning or interruptions in the system services. Like that, some technical clarity of classifying it, categorizing it, reconfiguring it so that the need and other requirements are fulfilled by this intelligence. These few of the aspects, nothing but prevention of certain probable cause or probable fault, probable any defect is postponed. It is not guaranteed that it will never occur. It will postpone, it will reduce the impact of such occurrences such that system will be under your control. Then we call them as preventive measures or preventive control, which the impact of such a massive phenomena is diminished or postponed to certain duration. These mechanisms ensure such effects. Similarly, when I say emergency control, which we are speaking, the word emergency is very critical. It is a measure taken to stop worsening of any such adverse situation. Already system is worse. System is having a multiple problems, multiple point range violation. Many components are working neck to neck at critical points. Further, any decision adverse if taken, situation will be worsened. That situation can be avoided, situational effects can be minimized and prevented further degradation, further cascaded failure, etc., which can bring the system back to a controllable state wherein it can be brought coolly back to normal. Like an under frequency, under voltage, load shedding, etc. are the common emergency control which we have here. Tripping of generator. Suppose a situation, heavy load is noticed, very big fault has really caused a massive fault, power is flowing down to the earth. Definitely this will spoil transmission, equipment, generator, like that, tripping of generator. Cut off the generator so that at least the generator is protected from such hazards. What the things got lost, let it be lost. At least the tripping of generator prevents generator failure. Like this emergency, it is critical that decision is to protect the generator. Rest of the system or other part of the connect system already worsened, gone out of your control. At least save this. This kind of tripping of generator would be a one choice. Load shedding. Load is such a massive on this. Suddenly, in steps or in a proper mechanism, remove the load at least so that load is isolated from the generating area and at least generation setup is safer in that perspective. This is how load shedding, removal. Scheduling is reorganizing. Shedding means exactly removing it. Fast valving or fast water diversion, which leads to a fast reduction in generator. This is another countermeasure during this emergency situation where generation is reduced by reducing the input fuel to the turbine. I can divert the input fuel on other side so that input fuel hitting on the turbine blade is minimized and definitely generation output is minimized. It is to safeguard the generation to bring it to halt state. So fast valving is to make the valve mechanism divert the water to the other side, reduce the input fuel to the turbine so that acceleration which is already reached will be bringing down slowly. Another one important fact I would like to discuss with you. As there is a tremendous demand in the particular requirement, the quite natural phenomena is to raise the input fuel. If there is a dip in frequency due to the additional load megawatt, the frequency has fallen down. The countermeasures in the control system is to increase the input fuel, open the valve so that more fuel enters the turbine blades and turbine accelerates more and more like that. If the load increases on the generating load increases on the power system, definitely frequency falls down. That demand more input. So more and more opening up of the valve make a runaway speed in the mechanism, which is a dangerous mechanism. These rotating machines may get damaged. Therefore, when there is a tremendous demand, the valving has to be done properly, divert and control the generation. Then control the disconnection and the interconnection of system. Prevent spreading of frequency problems. This is, I have to disconnect the load in steps gradually in a proper fashion so that frequency deviation will not be spread to a large area, it will come under the control. And controlled is islanding, controlling the islanding to create local generation and load balance. It means there is a segregate the areas, a area of a generator only, area of load only, substation. It's called islanding. So islands must be isolated and each island has to be operated independently to the possible extent so that there is a disconnection from one to one, so that prevention at that point can be addressed carefully. Blocking of cap changer. Don't allow cap changer to simply shift and try to boost the voltage. Otherwise, transformers get lost. So block the tap changer so that such a mechanism prevents the emergency. And fast HVDC power transfer control. Make the HVDC transfer to control appropriately so that such an adverse effect, adverse phenomenon is brought to the control. Application of braking resistor. These are the set of resistors hooked across the generator to short the output to the ground. It is nothing but braking resistor. The enormous energy which is available in the generator is dumped to the earth via this resistor. We call them as braking resistor. So these are a set of resistors available in generator area where certain critical situation generator has to be stopped. Braking has to happen. Stopping has to happen. Hook these resistors across the armature terminal so that will drain or that will get connected to the earth. That will be a deceleration effect on the rotating object, and rotating object comes down to slowly stand still. In this way, these are the few emergency controls which are being exercised. Then in the next class, we'll just see how control problems are put with a timestamp and further window. Okay. Right now, I just close my session and we'll interact in the further session.